Hi guys, this is for Unit 2, Module 4.2, Constructing Arithmetic Sequences. The essential question, what is an arithmetic sequence? A short answer, an arithmetic sequence is a sequence in which difference between any pair of consecutive terms is constant. And this is also connected with functions, constant rate of change, and things that you've seen in previous year. Now, first example, so we're exploring an arithmetic sequence. Um, let's look at context. All right, context matters. The story matters. You can order tickets for a local theater online. There is a fee of $2 per order. Per order. Okay, so I'm already thinking like this is probably my rate. Okay, rate of change back in the day, right? Now matinees tickets cost $20 each. The total cost in dollars of ordering in tickets or matinee tickets online can be found with this. Okay, so it looks like our initial value, okay, where we start is $2. So just for ordering tickets, you have to pay $2. Okay, now how many tickets is totally up to you. Okay, and that's represented by in. Okay, they do cost $10 per ticket. Now the table shows the cost of 1, 2, 3, and 4 tickets. Okay, so this would actually be our domain. Okay, in this situation, maybe you're buying one ticket for sure, maybe two tickets with a friend, maybe your friend has another friend, or maybe you're just getting all your family members. All right, so either way, that's your domain. You have 1, 2, 3, or 4 tickets going on. Okay, now if you bought one ticket, and this is where the table will come in handy. If you haven't started trying this right now, if you're just getting used to this information, this is a good habit to have. And I'm sorry, we're actually using C of N, right? Cost of number of tickets. So let me correct that real quick because I'm trying to focus on function notation, even though we're talking about sequences. All right, and the rule. Our rule here is 10 times N plus 2. Now, if you're buying one ticket, you're going to have 10 times N, which is going to be 1, plus 2. 10 times 1 is 10, and 10 plus 2 is 12. So we're going to have 12. You can do the same thing here with 2 tickets. We use the same rule for substitution, just like we did with functions. And we have 20 plus 2, which is 22. So notice how I'm just going through here. Now, if you haven't noticed already, tickets cost what? $10 a piece. So it's no surprise that our difference here between the ticket costs is $10. If you want to double check, we can keep doing this algebra, which is totally fine and practical. And it looks like our assumption is holding true. So don't be shy of using tables. There we go. Yep, looks like we're going up by tens. So let me finish the table over here. Now, they're talking about range. Range, again, is cost, okay, the total cost. So our range is, well, buy one ticket, get $12, or cost $12. 2 tickets will cost $22. 3 tickets will cost $32. And 4 tickets will cost $42. So this is along the lines of input and output, okay? So, oops, I'm sorry, that is wrong. Let me explain why. What we put in is the number of tickets, right? The number of tickets is what we put in. We put in 1, out came 12, right? So we put in 1, out came 12. So tickets is the input, and total cost is the output. All right, what is the first term of the sequence? In this situation, our first term in the sequence is 12, okay? So 12 was the first that we got in our sequence, okay? All right, so let's look at definitions. An arithmetic sequence. Oops, sorry. There we go. Click the wrong button. There we go. In arithmetic sequence, come on, highlighter. There we go. In arithmetic sequence, the difference between consecutive terms is always equal. Okay, so in my last example, our difference was 10. We kept going up by tens. The difference is written as D, okay, which is also known as common difference. So we had a common difference in the previous example of $10. Now, an arithmetic sequence can be described in two ways, explicitly or recursively, okay? Now, as we saw earlier, in an explicit rule for a sequence, the nth term of an arithmetic sequence is defined as a function of n. Now, in recursive rule for a sequence, the first term of the sequence is given, and the n term is defined by relating it to the previous term, which is something that we have practiced. So let's get a little bit more familiar with both rules. So if you look right here, the general recursive rule is where do we start, right? So we, for example, have f of 1, and our first term was what, $12, right? And then we had our function of whatever our previous term was plus our difference, which was $10. So that would be the recursive for the last example that we saw. Now, for explicit rule, all we have to do, and don't forget to state this, n is greater than, whoa, go back. There we go. Sorry, technical difficulties. Click the button on my little pen. There we go. So make sure you state that, because now you're stating that we're going beyond just 2 or 3 numbers. Okay, going back to explicit, f of n equals our first term, which was 12, plus our difference, which was $10, times n minus 1. And this would be explicit. So these two rules really do say the same thing, just in a different way, okay? One's more of a function, and the other one is really just showing that that there's a sequence between the last number. All right, example 2. We're writing the recursive rule and the explicit rule for the sequence described by the table below. So a savings account starts with $2,000, and $500 is deposited each month. Sorry. So we start off with 20,000 or 2,000, and we go up by a constant or a common difference of $500. Now, is that constant? Yeah, we keep on going up by $500. Okay, so what do you think our common difference is? That's right, $500. So our recursive rule. Okay, let's start with our big bracket. Our first number in our sequence is the exact same amount of money that we start off with in our story, $2,000. And then our rule is represented by, well, f of n equals the function of n minus 1, which is really just saying the last term, plus our difference, which is 500. And that is for when n is greater or equal to 2. Okay, so that's something to note. Now, for the explicit rule, we have f of n equals, what was our first number, our first term? 2,000, plus our difference, which was 500, times our number, minus 1. Okay, so if you wanted to plug in, for example, if you were to do a table and you wanted to find out f of 1, or if you wanted to test this function notation, you would have $2,000, okay, your first term, plus 500, substitute in the 1 for n, and we end up getting 2,000 plus 500. 1 minus 1 is 0. Anything times 0 is 0. So f of 1 is literally just 2,000. So that's a great way to double check to make sure that you set up the explicit rule correctly. All right, your turn number 1. So go off this table, ask yourself, what's my first term? Okay, where am I starting? And what's my difference? Okay, so definitely figure that out first. So first term, what's your common difference? Okay, use the fill in the blank aspects of things. And then write your rules. So they kind of already set up the recursive rule. Okay, so don't forget your difference goes here. F of 1 is again your first number. Then the explicit rule. Now something to note is that make sure you use this for explicit. F of 1 plus your difference times n minus 1. Just ignore how they set it up here from the book. Okay, so remember this just means this is where you plug in the term that you're looking for. Okay, so if you were to use this for your next term, term 2 is 6,000. How did I get that? I looked at the table up here. Okay, if I was to test out my rule, I'd have 5,000 plus my difference, which they go ahead and already say is 1,000 because they were nice to follow through with that. Of course, you can always see the common difference here. Okay. And we're looking for the second term, which is 2 minus 1, right? So we're looking for the second term. So that's 2. That's how we got the 2 there instead of the n. 2 minus 1 is 1. And 1 times 1,000 is 1,000. And 5,000 plus 1,000 is 6,000. Okay, which makes sense because there's your second term, 6,000. And it's dollars. All right, so since d is always multiplied by the number equal to what? So try to talk to your group members about that. You could generalize this rule for the explicit. And I already kind of wrote it up here. You just have to figure out what f of 1 is and what your difference is times the n minus 1. All right, example 3. So this is just given the sequence, no fancy tables, nothing like that. Just the sequence itself. So let's find the recursive and then we will find the explicit. Now, first things first, let me see. My first term is definitely $100 or 100 something. And my difference, I went down by 12, it looks like. Did I go down by 12 here? Looks like I did. And last but not least, let's double check. So yeah, looks like I have a common difference of negative 12. That's possible. Sequences, numbers can get smaller and smaller as time goes by. It happens. So, recursive. Okay, so we have to do the bracket. Recursive is the one with the big bracket. We have to state what our first term is. That was 100. And now we have our setup. F of n should equal whatever our last term was, our previous term, which is represented by f times n minus 1, plus our difference, which is, well, negative 12. And, well, when you add a negative 12, really you're just subtracting. So instead of just saying plus negative 12, we can say minus 12. Okay? Now, let's handle the explicit. All right. So let's see. First things first, we need our function of n equals our first number, right? Plus our difference times n minus 1. So f of n equals our first term, which is 100, plus our difference, which is really just minus 12, or negative 12. So it's going to be minus 12 times n minus 1. You can always double check with a table and start substituting in for your new values for your sequence. All right, your turn number 2. Go ahead and do the same thing. So identify the recursive and the explicit rules. Okay, again, what's your first term? What's your difference? And then just go from there. All right, relating arithmetic sequences and functions. These are two conversations these are two different parts in the conversation that share the same equation or conversation. I'm sorry. They are the same leaf, or this they're two different leaves on the same branch, if that makes sense. It's very, very similar, just different ways of seeing it. Now, if we look at this situation, the cost of whitewater rafting trip depends on the number of passengers. Okay, so cost depends on the number of passengers. So our passengers will be um, our independent, and our cost is the dependent. Okay, input output still exists just like with functions, and that's because sequences are very, very similar to functions. Okay, they are functions in several ways. Now, if you notice, they do plot. If we had one person, okay, it would cost 75 bucks. If it costs two people, it costs 100 bucks. And you can see them plot this from the sequence. Three people cost 125, four people 150. So this is an arithmetic sequence. If you notice, what is our common difference? 25. We keep going up by a common difference of $25. So notice how this is a function, yeah, but it's also a sequence. There's a pattern that we can predict. All right, so your turn number 3. Go ahead and look here at our situation. We have seats in an auditorium, and that depends what row it is. So the first row has 6 seats. Okay. And then basically just second row, the third row, and so on. See if there's a common difference. All right, so go ahead and complete that table. Now, after you do that, I want you to find the difference. Don't forget, always start with what's your first term in the sequence. Okay, I already wrote it. There you go, 6. Okay, and go ahead and try to write the recursive rule for this situation. Test yourself, see if you can do it. And then try to write the explicit. The explicit rule. So recursive and then the explicit. All right, guys, have a great day. If you have any questions, let me know.